Hello everyone, welcome to my video about the properties of curves. What will be covered in this video are the following: how the first and second derivative play into finding out the properties of curves, what stationary points are and how to calculate for them, what local maximum and minimum points are, what inflection points are and how to calculate for them, what concavity is and how it relates to inflection points, and what a sign diagram is. What is the difference between an increasing and decreasing function, how to figure out when a function is increasing and or decreasing, and what a tangent is when it comes to properties of curves. The first derivative. When it comes to properties of curves, finding the first derivative of the function and making it equal to 0 will help you solve for stationary points, which are maximum, minimum, and stationary inflection points. Stationary points have a slope equal to 0. The first derivative will also tell you which parts of the function are increasing and which part of the functions may be decreasing. The second derivative. When it comes to properties of curves, finding the second derivative of the function and making it equal to 0 will help you solve for the inflection points, which are specifically the points where the concavity of the function of the graph changes. Now here are some examples of stationary points graphs. On the left, we have a maximum point graph, which is showing how the graph is going from positive to negative, which would mean that the function would be increasing and then at this point would change to be decreasing. On the right, we have a graph for a minimum point, which is changing the graph from negative to positive, which could also be said that the function was decreasing and then after this point is increasing. We have a stationary inflection point graph, which is going from negative to positive, or it could be said for a function, the function was decreasing, and after this point, it has thus begun increasing. Here are examples of increasing and decreasing function graphs. So on the left, we have an increasing function graph, which happens when the first derivative is greater than 0. And on the right, we have a decreasing function graph, which happens when the derivative is less than 0. Finally, here is an inflection points graph. This graph shows what are considered inflection points, which is the point where the concavity of the graph changes, as on the left the concavity goes from up to down, and on the right it goes from down to up. Let's try a problem. The function is equal to 4x cubed plus 6x squared minus 24x. Find the stationary points for this function. Let's begin by taking the first derivative, which will be 12x squared plus 12x minus 24. Then make it equal to 0. Now that we've made it equal to 0, let's factor it out. 6x plus 12 times 2x minus 2. Now we're going to solve for x. Take each part of the function out and set it equal to 0. We get that x equals negative 2 and x equals 1. So when x equals negative 2 or x equals 1, the slope is 0. And these points are either a maximum, minimum, or a stationary inflection point. But how do we know what it is? We know what it is by using a sign diagram. It is a number line that includes the x values that have been solved for. The plus or minus or above are the intervals where the function is increasing or decreasing. You figure out these intervals by plugging a number below the x value, as for example negative 2. If you plugged in a number lower than negative 2, such as negative 3, into the equation and ended up with a negative answer, you will put a negative above to show that the function is decreasing up to negative 2. So you can see, however, when you go to the right of negative 2, let's say you were to plug in negative 1.5, and it turns out that the function becomes positive, that shows that negative 2 has switched the graph from one that is decreasing to one that is increasing. So our x values are negative 2 and 1. Let's plug in negative 3. 6 times negative 3 plus 12 is negative. 2 times negative 3 minus 2 is also negative. A negative times a negative is a positive. So we know the function is increasing prior to negative 2. Now let's plug in a number between negative 2 and 1. Let's try out 0. 6 times 0 is 0, plus 12 is 12. 2 times 0 is 0, minus 2 is negative 2. A positive times a negative, 12 times negative 2 is equal to a negative. So we know that the function is thus decreasing past negative 2 and up to 1. Now let's plug in a number greater than 1. Let's try out 2. 2 times 6 plus 12 is a positive. 2 times 2 minus 2 is also a positive. Thus, we get a positive answer. Thus, after the function has passed 1, the function has thus begun increasing. So, we know that negative 2 is a maximum point, as the function is increasing before it and then decreasing after it. 1 is a minimum point, as the function is decreasing prior to it and then increasing once it has passed that point. We know that the first derivative is greater than 0, the function is increasing between negative infinity to negative 2, and 1 to positive infinity. We know that the first derivative is less than 0, the function is decreasing between negative 2 and 1. As you can see, negative 2 and 1 have brackets around them. That is because they are a defined point on the graph. Infinity is never a defined point. So that is why you use parentheses instead of brackets. Now, using the same problem as before, let's find out the inflection points for this function. We know that the first derivative is 12x squared plus 12x minus 24. That makes the second derivative 24x plus 12. Let's put it equal to 0, which helps us factor it out. As in this case, 12 is a common factor between 24x and 12. Now let's solve for x by making each part of the function equal to 0. We know that x equals negative 1/2. We also know x always equals 0 when it is a constant times the function. So our 2 points are actually x equals 0 and x equals negative 1/2. Now let's use the sign diagram to figure out the concavity of the graph, as inflection points tell us this. We have written negative 1/2 and 0 on our sign diagram. Now let's plug in a number lower than negative 1/2, which is negative 1. We know that the constant is positive, so plugging negative 1 into the inside function, you get a negative answer. So a negative times a positive is a negative. Thus, the graph has a downwards concavity up to negative 1/2. Now let's plug in a number between negative 1/2 and 0. Let's plug in negative 1/4. We still have a positive from 12, and the inside actually becomes positive as you plug in negative 1/4. Thus, you get a positive answer. Thus, the concavity of the graph is now upwards. And finally, let's plug in a number greater than 0. Let's do 1. The outside is always positive, and the inside this time also gets us a positive. So negative 1/2 is a non-stationary inflection point that changes the concavity from down to up. 0 is a non-stationary inflection point that confirms that the concavity is up forever. Now here's the graph of 4x cubed plus 6x squared minus 24x. We know that when x equals negative 2, we have a maximum point. When x equals 1, we have a minimum point. When x equals negative 1/2, we have an inflection point that changes the concavity from down to up. And when we have x equaling 0, we have an inflection point that confirms the upwards concavity. Now let's add the first derivative graph, 12x squared plus 12x minus 24. The graph of the first derivative crosses the x-axis at x equals negative 2 and x equals 1. Since f of x tells us the stationary points, we know that when x equals negative 2, we have a maximum point, as the graph is falling below the x-axis. Meaning, if you look at the graph, at negative 2, the graph has gone from being above the x-axis in the positive region to then being below the x-axis, the negative region. We also know that when x equals 1, we have a minimum point, as the graph is heading above the x-axis. We're going from the negative region to the positive region of the graph. Now let's add the second derivative graph, 24x plus 12. The graph of the second derivative crosses the x-axis at x equals negative 0.5. Since the second derivative tells us the inflection points are concavity changers, having all the x values below x equals negative 0.5 have their y values also below the x-axis, and then above as the x values go above x equals negative 0.5, it shows that this inflection point is changing the concavity from down to up. We also know that when x equals negative 2 or x equals 1, we have a global maximum and minimum, as the first derivative did not cross the x-axis again. If it had, we would have had a local maximum or minimum. We can figure out if a maximum or minimum is local through seeing with the sign diagrams for the first or second derivative if the function ever increases, decreases, or has a concavity change later on. If it did, it would show that there was a possibility for another maximum or minimum that would probably be the global. Now, things to know. When you have a function that requires the quotient rule to be used to get its derivatives, the part of the function in the denominator's x's will be vertical asymptotes. Here's an example of a problem with vertical asymptotes. Since negative 2 and negative 6 come from the denominator part of the equation, they are vertical asymptotes. As you can see, the intervals involving negative 6 or negative 2, negative 6 and negative 2 are surrounded by parentheses, as they are not a defined point on the graph. The graph actually can never be equal to those points as they are vertical asymptotes. When a point has a slope equal to 0, as stationary points do, the tangent function of that point will be equal to 0. When a problem is asking you to solve for critical points, it is asking you to solve for the stationary points, inflection points, and vertical asymptotes, if they are present. And when a problem asks you to show algebraically when a function is increasing or decreasing, show how the first derivative is greater than 0 for increasing, and the first derivative is less than 0 when decreasing. Now try this problem on your own. The function equals 16x cubed plus 36x squared plus 8. Find all the critical points of this function. Pause this video and solve this problem on your own. Once you have solved it, check your work by continuing to play this video. And that is all for today, everyone. I hope you enjoyed this presentation and you found it educational and learned something. Talk to y'all later.